Welcome back to the Deep Dive. Today we're tackling someone truly, well, mind-bending. Giordano Bruno, a Renaissance thinker who, way before telescopes, basically kicked the universe wide open.
He really did. It's like he demanded a physics that was big enough to actually contain the cosmos he imagined.
Exactly. And that's our focus today. Bruno's incredible cosmology, this vision of an infinite, centerless universe packed with worlds.
And what's really fascinating is how these sort of intuitive leaps he made centuries ago are finding real echoes, even validation in modern physics, specifically through something called motion theory.
Right, so our mission, our deep dive here, is to pull out the key bits from Bruno's thought and really connect them to how we see the universe now scientifically.
We want to show you how this 16th century philosopher's, well, sheer defiance in a way, prefigured how we even do science today.
Prepare for some potential aha moments, maybe a shift in how you picture reality itself.
It's definitely a trip worth taking. His ideas about the fundamental nature of things, yeah, they stick with you.
Okay, let's properly dig in. Bruno's core ideas, especially from his book on the infinite universe and worlds around 1584, they weren't just adjustments, they were revolutionary.
Oh, completely. He threw out the rule book. We can boil it down to maybe 4 huge claims.
Go for it. What were they?
First, the universe, infinite, no center, Earth isn't special, just one spot among, well, infinite spots.
Wow, okay, straight out of the gate, that's huge. What's number 2?
Second, those stars you see, they're suns, just like ours. And many probably have planets orbiting them, other Earths. He even floated the idea they might be inhabited.
Centuries before exoplanets were even a concept. Incredible. Number 3.
Third, forget those solid crystal spheres holding everything up. Nope. The heavens, he said, are fluid. It's all about motion, continuous change.
So no rigid clockwork, just dynamic movement. Makes sense. The last one.
Fourth, nature is one single living whole. Things that look like opposites, hot, cold, big, small, are just aspects of the same underlying process. Everything's connected.
You really feel the intellectual shockwave in that package.
Yeah.
Abolish the roof, get rid of the central throne, let motion just run free.
No metaphysical fences, as he put it earlier. It must have been such a radical shift in perspective for anyone listening then.
But, and this is the big but for me, how? How did he get there? No telescopes, no modern math.
Yeah.
What was he building on?
That's the million-dollar question, isn't it? It boils down to his, let's call them core constructions, ways of reasoning.
Okay, constructions. Like what?
So for the plurality of worlds, all those other planets, he used this kind of proto-correspondence principle. Simple logic, really.
How so?
If our sun is a star, and stars look like our sun, well, doesn't it make sense that nature would sort of repeat its grammar? Worlds become the logical consequence, not some weird exception.
Ah, so nature repeats its grammar. I like that. If it happens here, why not elsewhere? Makes sense.
Exactly. For centerlessness, his logic was a center means a boundary, right? Something to be the center of. But if the cosmos is infinite, no boundary, therefore no center. Concepts like up or down become totally local, relative. Position is just about how things are moving in relation to each other.
So position isn't absolute, it's relational. That's a profound shift from the old fixed spheres idea.
Huge shift. And that ties into his third point. No crystal spheres. He just couldn't see the heavens as this rigid, unchanging structure. He imagined bodies moving freely in some kind of continuous medium, dynamic, not static.
It feels much more alive somehow.
It does. And that connects to his fourth idea, the unity of opposites. He felt the very small and the very large must be linked by the same fundamental rules, the same underlying rhythm or motion grammar, repeating across scale.
Like a universal pattern echoing everywhere.
Sort of, yeah. Like the universe has a consistent way of operating from the tiniest speck to the grandest structure.
Okay, this is where it gets really wild for me. Because so much of this sounds incredibly modern. It's like he had a peek into 21st century astronomy.
It is uncanny, isn't it? Let's look at what aged well and how motion theory gives us the how.
Yes, please. Let's connect it.
Okay, first, cosmic pluralism. Bruno's innumerable worlds. That's just standard astronomy now. Exoplanets are confirmed. They're everywhere. Stellar systems are the norm.
We have the data now. Thousands of them.
Exactly. And motion theory explains why they're common. It suggests the same basic processes, what we call synchronization grammars, like accretion, orbital resonance, energy dissipation. They just repeat everywhere. Building worlds is generic.
So the grammar is portable. It works across the universe.
Yeah.
Okay. What about no center?
Well, modern cosmology agrees. No center. Instead, we see this large-scale, homogeneous, isotropic expansion looks the same everywhere, expanding uniformly.
Right. The Hubble expansion.
Motion theory adds a layer. It says that expansion is like the baseline state, low synchronization. Gravity then isn't some mysterious force, but just local convergence things pulling together towards higher synchronization density. That's what makes galaxy stars structure.
So gravity carves things out of the general expansion. Interesting. And the dynamic heavens.
Oh, absolutely confirmed. Space isn't empty, it's buzzing. Radiation, plasma winds, magnetic fields, warped space-time.
Definitely no crystal spheres.
Not even close. Motion theory goes further. Space is the motion. It's the dynamic background that carries everything else. It's never empty, never still, just constant change.
That's a powerful image. Space as the motion itself.
And remember his unity of opposites, the scale echoes. We see that too. Look at planetary systems, the resonant orbits of moons like Jupiter's. Then look at galaxies, the spiral arms, the bars.
Similar patterns.
Similar mathematical relationships, yes. The same kinds of wave locking, the same bifurcation showing up at vastly different scales. It's like Bruno's correspondence by rhythm made concrete.
So motion theory's core ideas tie into this.
All right, remember, everything is structured motion. Gravity is convergence toward denser synchronization. Fields are just gradients, slopes in that motion.
Okay, I think I'm getting the connection. But Bruno wasn't always right, surely. He was working centuries ago. Where did he maybe push it too far or miss the mark?
Absolutely, and that's important too. His cosmology was brilliant, but largely metaphysical, philosophical. The actual evidence in 1600, pretty thin, let's be honest.
He couldn't point to data points for infinite worlds.
Exactly, and he invoked a kind of universal soul animating things. Poetic, powerful, but, well, not really testable, scientifically speaking. Motion theory keeps the core idea that motion is fundamental, but drops the untestable animation aspect.
Sticks to the physics, basically.
Right. Also, his insistence on infinity. Scientifically, can we really tell the difference between a truly infinite universe and one just unimaginably bigger than what we can see?
Good point. Our observable horizon is finite.
So motion theory tends to treat infinite as a useful concept in the math, a modeling tool, unless a specific prediction depends on it being literally true versus just very, very large.
A pragmatic approach. Any other areas?
The big one is mechanism gaps. He just didn't have the concepts we rely on now. Gravity, as we understand it, inertia, conservation laws.
The mathematical machinery was missing.
Precisely. His picture had the right overall shape, the right contour, but lacked the engine underneath the action principles that generate the specific numbers and predictions. Motion theory aims to provide that engine, deriving things like general relativity, electromagnetism, even quantum mechanics from fundamental motion principles.
So motion theory is like adding the detailed physics equations to Bruno's grand architectural blueprint.
That's a great way to put it. It supplies the precise, testable framework that Bruno's amazing vision understandably lacked. It bridges that gap from intuition to testable science.
Okay, so let's make that bridge explicit. How does motion theory translate Bruno's big ideas into, science we can actually do? What's the vocabulary shift?
Let's translate. Bruno's plurality of worlds. In motion theory, that becomes grammar portability, meaning the fundamental rules, the grammar of how motion organizes itself into stable patterns like cooling gas, accreting matter, shedding spin, interacting with light. These rules are universal. Worlds are just where that grammar successfully creates a long-lived structure. No special pleading for Earth needed.
So planet formation is a natural, repeatable outcome of these universal motion rules.
Got it.
Centerlessness.
That becomes relational bookkeeping. There's no absolute grid, no cosmic origin point for motion. All our measurements, our clocks, our rulers, they're just local devices comparing relative motions, local synchronies. The motion itself defines the relationships, the coordinates.
It's all relative, built from the interactions themselves.
Okay.
And the living unity.
That maps onto the idea of a coherence network. Instead of a single world soul, think of interconnected networks of synchronized oscillators, everything coupled from atoms vibrating together to entire ecosystems.
Like everything is humming together, connected by these motion patterns.
Exactly. And life could be seen as a special kind of region within that network, one where feedback loops get really complex, allowing patterns to preserve themselves, adapt, and increase their synchronization density. It's all interconnected motion.
This is powerful stuff.
Yeah.
But how do we test it? How do we take these ideas, Bruno's intuitions, filtered through motion theory, and design actual experiments or observations for, say, 2025?
Excellent question. That's the crucial step. We can frame specific falsifiable tests.
Like what? Give me an example.
Okay, exoplanet abundance and architecture. Using motion theory, we could predict not just that exoplanets exist, but their expected arrangements, the distribution of their orbital periods, how elliptical their orbits are, their inclinations, based on simple rules of desiccation and resonance capture.
And then compare those predictions to the real data pouring in from tests, James Webb, etc.
Precisely. Bruno bet worlds are common? Motion theory adds the math for how they should be arranged. If the predictions match the data significantly better than random chance, that's strong support.
Okay, that's concrete. What else?
Testing isotropy without a throne. We can use gravitational wave events, those standard sirens and supernovae, to map the universe's expansion with incredible precision. Motion theory predicts that any tiny deviations from perfect smoothness won't point to a cosmic center, but will align with known local structures, like galaxy clusters or large-scale flows.
So local gravitational lumps explain deviations, not some overall cosmic tilt.
Exactly. We could also build a scale echo atlas. Catalog phase locking across scales, moon resonances, galaxy bar speeds, maybe even stellar pulsation modes. Motion theory predicts specific preferred mathematical ratios should dominate these locked systems. Are they there, or is it random?
Checking for that repeating rhythm Bruno sensed.
Spot on, and related to life. Biosignature risk accounting. Use motion theory to model planetary environments. Predict which potential biosignatures, like oxygen plus methane, are most likely, but also rigorously estimate how often geology alone could fake those signatures.
Turning Bruno's hunch about life into a careful, statistically sound search strategy. Less guesswork, more calculation.
You got it. And finally, a no hard spheres test. Quantify how things like galaxy cluster edges or the heliosphere around our sun are shaped. Motion theory says they should be smooth gradients in motion properties, not sharp physical walls. We can test that with plasma physics and observations.
These are real, tough tests. It grounds the whole thing.
That's the goal. Honor the intuition, but demand empirical rigor.
It's worth pausing for a moment, though, to remember the man himself. Giordano Bruno, born 1548 in Nola, Italy, became a Dominican friar, but his ideas quickly got him into trouble.
Yeah, he spent years basically on the run, debating, writing, challenging authority across Europe: Geneva, Paris, London, Prague.
His cosmology, his views on an infinite universe with moving worlds, combined with other theological challenges.
Yeah.
It didn't end well.
No, he faced the Roman Inquisition, was imprisoned for years, refused to recant his core beliefs, and ultimately, well, he was burned at the stake in Rome in 1600. A martyr for his ideas.
That context is chilling, but vital. His intellectual courage was immense.
Absolutely, and whether every detail holds up or not, that courage is the enduring lesson. Always be willing to enlarge the frame until it fits the motion you suspect is there. Don't let dogma box you in.
So wrapping up this deep dive, Bruno's impact feels immense. He didn't just nudge the Earth out of the center. He, as you said, erased the ceiling. Plurality, centerlessness, dynamism, those were his gifts.
And motion theory takes those gifts, those pillars, and bolts them firmly to a modern scientific structure.
Right. Worlds are common becomes testable predictions about planet arrangements.
No center becomes specific tests using gravitational waves and cosmic expansion data.
No crystal spheres becomes a physics of gradients in a dynamic, moving substrate.
It gives us the tools to actually work with his insights.
So the real takeaway, maybe, isn't just celebrating Bruno, but using his approach, refined by motion theory, as a method, a way to question our own assumptions.
Exactly. Wherever you see a wall in your understanding, ask, is it really a wall or just a steep gradient?
Wherever you see a center, ask, is it truly absolute or just a local point of stability, a convergence?
Wherever you see something unique, a special case, ask, what underlying universal grammar could actually make this generic, make this expected?
Bruno guessed the grammar. Motion theory supplies the score and the metronome.
Beautifully put.
So the thought to leave you with, what walls, centers, or special cases in your own understanding of the universe or maybe anything else might just be waiting for you to see the underlying motion, the dynamic pattern? Something to think about.